So we're going to talk about molar concentration or molarity in this video. To start out with, the formula for molar concentration, or any type of concentration, is the amount of solute divided by the volume of solution. So it's really how much solute is dissolved in a volume of solution. So at this point we have talked about percent mass over mass. We have talked about percent mass over volume, percent volume over volume, ppm, ppb, and all those have to deal with either mass or volume of solute dissolved in a volume of solution. ppm and ppb is just a type of mass solution. But at this point, we're going to go into molar concentration. So, molar concentration has a very specific formula. It's still amount of solute over amount of solvent, but it's moles of solute, volume of solution, in a volume of solution. So the C in this equation is not just any type of concentration, but molar concentration, also called molarity. And the units has to be in moles per liter. So moles meaning moles of solute. Liters meaning liters of the final solution that you have made. Okay, so let's try an example. What is the concentration of the solution made from 7.50 grams of calcium chloride dissolved in 2 liters of water? Okay. So when they say that when they say you have 7.50 grams of calcium chloride, that means they're measuring it as a solid. That means they're measuring it as a salt. Okay, so when you're adding, so if you picture this, you have 2 liters of water, and you're adding 7.5 grams of calcium chloride into it. Because calcium chloride is an ionic compound, and it will dissociate when it dissolves, and the amount is so little anyways, the volume of the solution that's made does not change. So you would think that adding this many grams of calcium chloride would increase the volume of the solution and made it something like maybe 2 liters and 3 mils. But actually it doesn't change the volume of solution. So even though they said 2 liters of water, you can pretty much take it as 2 liters of solution. Okay, so using our equation, C equals N over V, and again, this N is moles of solute, so moles of CaCl2, meaning that our first step is actually to calculate moles of CaCl2. So moles is calculated by taking the mass divided by the molar mass, which equals to 7.5 grams divided by the molar mass of calcium chloride which is 110.984 grams per mole. So that gives us 0.06758 moles of calcium chloride that's dissolved. So at this point I'm not going to round yet because that's not my last step. My second step is to take this amount of moles and divide it by the volume of the solution. So we have 0.06758 moles dissolved in 2 liters of solution. Which is equal to 0.0338 moles per liter. So what we're saying is, yes, there are 2 liters and there is 0.06758 moles dissolved in it, but when we talk about molarity, it's always a ratio of put in terms of per 1 liter. So that means in every liter of solution, there is 0.0338 moles of calcium chloride dissolved. So in order to make a comparison of different solutions, it's not useful to say, oh, there is this many moles dissolved in this beaker, that's 2 liters, and then there is this many moles dissolved in that beaker, that's only 1 liter. You cannot compare concentration when you have different volumes, which is why concentration is always put into per liter, and that makes it easy to compare different solutions or different concentrations. So therefore, the concentration of the solution is 0.0338 moles per liter. Okay, so that should be one of the simplest molar concentration calculations that you will see, where they gave you a mass, you have to change it to moles and then just use the equation to figure out the concentration. Let's try another question. What mass of NaCl is required to make 250 mL of a 0.5 molar solution? So here, we're sort of going backwards because you can, if you picture this again, you have, I'll use beakers because it's simple, a solution of 250 mL, which I'll change to liters actually, and the concentration is 0.5 moles per liter. And they're asking you what mass of NaCl. So, in order to calculate mass, we need moles. So that means our first step is to calculate moles. If we look at that equation again, right, we can isolate for moles in this equation. So isolating for moles give us N equals C times V. That means that if you have a 0.5 moles per liter solution and you have 0.25 liters of it, then the amount of moles that will be inside is going to be 0.125 moles of solid. So remember that when you use this equation, it refers to moles of solute over volume of solution. Why does this work? So if you try to make sense of this, what it's saying is that in every liter of solution, there is 0.5 moles. But you don't have a liter of solution. You have 0.25, or in other words, a quarter of a liter of solution. So if 1 liter gives you 0.5 moles, in a quarter of a liter, it's going to contain 0.125 moles of the solute. Now that we have moles, we can use what we have learned before. Mass equals moles times molar mass to determine the mass of the solute that you have to add. So in order to make the solution, we need to add in 0.125 moles. But remember, in real life, there's no equipment to measure moles. Right? You have an electronic balance which will measure the mass, but there's no lab equipment to help you measure moles. So moles itself in a lab is not useful because we cannot measure this. But if we convert it to a mass, then we can measure this in the lab. So NaCl, the molar mass is 58.453 grams per mole. Multiply that together is 7.3 grams. So again, if we look at this, what we're saying is we know the concentration of the solution we want to make. We know how much we want to make of it. So when I'm making the solution, how many grams of the solid do I need in order to make the solution? So if we were to draw this, right, you can add in, here's my balance. You can add in 7.3 grams of salt and then step 2, you then take that 7.3 grams of salt and then you add in 250 mils of water. And if you were to do that, you would have a 0.5 molar solution. So therefore, 7.3 grams of NaCl is required to prepare 250 mils of a 0.5 molar solution. So here we're using the same equations as before, but you're just calculating mass instead of calculating concentration. Let's look at a last example. What volume of a 0.8 molar solution can be made with 1.23 grams of lithium nitrate? So again, 1.23 grams, that means you're measuring it as a solid. There's our solute. It's in the form of, in a state of solid. Otherwise, why would you measure grams, right? The only reason that you're measuring grams is because it's in a solid right now. Another thing, when they're using capital M as a unit, it's the same as saying moles per liter. So, what are we trying to do? They're saying that, I'm going to use a beaker again, even though this should not be made using a beaker. Okay, they're saying that you have added in 1.23 grams of lithium nitrate. You want to make at the end a 0.8 molar solution. So how much water do you have to add? So we can work with the same equations, C equals N over V. Okay, but we're not given moles, so we have to change 1.23 grams into moles. So first step, let's calculate moles of solute. Moles is equal to mass divided by molar mass, which is equal to 1.23 grams divided by lithium plus 1 nitrogen plus 3 oxygens molar mass, which is 68.941 grams per moles. So this is equivalent to 0.01784 moles. So that means you're adding 0.0184 moles in your solution. But at the end, again, you don't know what volume it is, but at the end, you know that your concentration has to be 0.8 moles per liter. So our volume is a big question mark. And we can isolate for volume in this equation by doing this. V equals N over C. So it equals 0.01784 moles divided by 0.8 moles per liter. That is going to give us 0.0223 liters. 3 significant digits, so we have 3 significant digits. So again, if you think about what you're actually doing, if you were to do this in a lab, right, you would dissolve 1.23 grams in, we now know that it's 0.0223 liters, which is equivalent to 22.3 mils. So if you were to dissolve 1.23 grams of lithium nitrate into 22.3 mils of solution, the resulting concentration is going to be 0.8 moles per liter. So therefore, 22.3 mils of solution should be prepared. Now, as an extension of this, so imagine you have made a solution. It's right now 0.8 molars because you have added, or the volume of solution is 22.3 mils. So we'll kind of make it like that. And then we'll represent the solute by these dots that I'm drawing. Sorry, I made the wrong unit here. Let's try that again. 0.8 moles per liter. Okay. And to do this, you added 1.23 grams. Is it 1.23? Yes, 1.23 grams of lithium nitrate. What if you made a mistake and you didn't add this many mils of water? Then how would that affect your concentration? So let's say instead you added more water. So let's bring it to, I don't know, 100 mils. So instead of adding this 22 mils, you have added almost 5 times as much water. So you can imagine that if you were using the same beaker and you haven't changed the amount of solid you're adding, okay, but now all of a sudden, so I represented this using 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 dots of solute. So the amount of solute hasn't changed because that's the amount you've added. But instead of spreading it out over this 22 mils of water, you're now spreading it out over this larger volume of water. So what will happen to the solute? Well, the same amount of 1.23 grams would now spread out. So in essence, when solid are allowed to spread out more, the concentration is going to lower. Concentration will be lowered. Why? Because your solid particles are spreading out. Are more spread out. Okay. So what are we really looking at when we're looking at concentration is I know even though that the volume of these two solutions are different, you don't look at the total volume. When we look at concentration, it's kind of like taking this one part of the solution. Right, so I know I didn't do a good job of spreading it out evenly, but taking the same part, same size of solution. So I'm trying to draw these squares so that they are roughly the same size, okay? And taking a look at how much solid is in this one equal volume, right? So this is a fair comparison. If you compare this size in this solution and the same size in the solution, regardless of what the total volume is, then you get a sense of how spread out or how concentrated the solute is in the overall solution.